how to calculate the LU factorization of a matrix. So we just spent the best part of an hour, both in the last lecture and this lecture, calculating L and calculating U. Now, what use is that, you may ask? Okay, the reason being is once we've got LU factorization of the coefficient matrix, it allows us to easily solve a linear system. So remember, when we calculate when we write down linear systems, we use matrix equation. A is your coefficient matrix, X is your unknown vector, B is your right-hand side vector. Well, remember, A equals LU. That's what we just done. So if we replace A with LU, we get this equation. And if we let Y equals U times X, okay, we get this equation. So what this means, okay, what this means is we can calculate this, the solution by solving Ly equals B. Now, L is a lower triangular matrix. That can be solved straightforward using forward substitution. So we solve Ly equals B using forward substitution. So starting at Y1, then going to Y2. You okay, guys? There's a bit, you know, a bit of a hustle here. So we do that using forward substitution. And then once we got Y, we solve Ux equals Y using backward substitution. So starting at X3, then go to X2, then go to X1 if you've got a 3x3 system. Okay, so let's have a look at that. Right, so this is an example in the notes. Okay, 3x3 system. Okay, and you've actually already done the LU factorization of this. Okay, this was from a previous example. Okay, and this is what we got. So we've already done the LU factorization. To solve, we first solve Ly equals B. Okay, so here's my L. It's my lower triangular matrix. This is my vector of Y's, and that's my right-hand side vector B. The first Y1 is always the first B because we have 1 there. So Y1 is minus 1. Y2, well, if we multiply this out, this means 2 lots of Y1 plus 1 lot of Y2 is equal to 5. So rearrange that, we got 5 minus 2Y, 1. Y1 was minus 1, so therefore we've got 5 plus 2 gives us 7. Do the same for Y3. We have minus 1 plus 3 lots of Y1 plus 1 lot of Y2. And that will give you 3. So forward substitution gives us our Y vector. Once we've got the Y vector, we use that in Ux equals Y and solve. So this vector here is your Y vector. Here's my U vector from the LU factorization. And we go backwards, we back substitute. So in this case, 1 x3 equals 3. So therefore x3 equals 3. x2, well, we have minus 1/10. So we have to divide through by minus 10. 7 plus 1 lot of x3. Okay, so that gives me minus 1. And finally, we've got minus 1 minus 3 lots of x2, which gives me 2. So the solution is x1 is 2, x2 is minus 1, x3 is 3. If I was to change the b vector, I could still use the same factorization. That's the beauty of this method. Okay, so quite often you do change the right-hand side vector, but don't change the coefficient vector. You don't have to go through all the Gaussian elimination again. You just use the L and U factorization. Okay, with that in mind, let's have a look at this example. Yes. I mean, this is pretty much the same as Gaussian elimination, but it just reduces. Yeah. Okay, guys, this is on page 96. So first thing we need to do is calculate the LU factorization of that. So how long is that going to take you? Sorry? See that matrix there? That's the coefficient matrix of that. So I'm allowing you to use that one. If you want me to be lazy, do it on MATLAB. Don't need to. You've already done it. Okay. So the first thing we do, okay, we solve Ly equals B. Okay, so your L, which we did earlier in true Blue Peter style. Okay, so that's what I need to solve. Because it's lower triangular, we can use forward substitution. Okay, so if we read across, this means 1 lot of y1 is equal to 14. So therefore, y1 is 14. Well, y2, what we have is 2 lots of y1 plus y2 is equal to 16. So we got 16 minus 2 lots of y2. What's 16 minus 28? Minus 12? I think so, minus 12. Okay, y3 now. So y3, we have 6 plus y1, which is 14, plus 4 lots of minus 12. So 6 plus 14 is 20, minus 48 is minus 28. And y4 is 20 minus 14 plus 12, oh dear, plus 3/8 times minus 28, which I think is 15/2. I just calculated that in my head. I certainly haven't got it written down. That's what I'd done earlier. Right, so that gives us our y4, straightforward forward substitution. So once you got your y's, I'm going to have to just quickly do okay. So once you got your y's, you then solve ux equals y. So you got our u from before. What we got? We got 1, 1, 3, 0. 1 minus 1 minus 3, 1. 0, 0, minus 8, 4. 0, 0, 5, 2. Okay. Okay, so now we go backwards. So solving for x4 first. Okay, so x4 is 15/2. Divide 5/2 gives me 3. x3, well, we've got a coefficient of x3 of minus 8. So I'm going to have whatever we have, I'm going to multiply by minus 1/8. So it's going to be minus 28 minus 4 times 3. Okay, so 4 times 3 is 12, times minus 28 is minus 40, and 8 for 40 is 5. x2 is going to be minus, because we've got a minus 1 there, minus 12 minus 3 plus 3 times 5. Okay, that looks like it's going to be 0. Okay. 12 minus 12 minus 3 is minus 15, but add 15 gives me 0. X1 is going to be 14 minus 3 lots of 5 minus 1 lots of 0. That's going to be minus 1. And that's the solution. So the solution to that 4 by 4 by LU factorization. First you factorize it, then you do forward substitution, then you do back substitution. What do you guys think of this method? Is it easy? Is it hard? I've got to admit, it's a bit awkward. Takes a bit of, it's a bit. But what's good about this is you can always check whether you got the right answer. With any form of algebra, well, I say any form of algebra, with simple linear systems, once you've got a solution, plug it back into the original system and you can check whether you got it right answer. If you were in an exam and you happen to be set this type of question, you could use MATLAB to help you. Okay. Sorry? What, the back substitution, forward substitution? You could do it in MATLAB if you want. If you do make a mistake, I won't be able to give you any marks for working. Yeah. If I was doing an exam, I'd write it down, but I'd check it on MATLAB, making sure I got it right. But if you just state the answer and the answer's right, brilliant, full marks. If you get one thing wrong, I can't give you anything because I haven't seen working. That's a very good question. If this was asked in an exam, if I was doing the exam, I'd write all this down. My personal thing. The reason being, let's say I've made one mistake, and I'm quite liable to make mistakes. Whoever's marking it, i.e. me, can give me some marks for working out. If you just do it all by MATLAB, put down the answer and the answer's wrong, I can't give you any working out marks. Sorry. So if this was an exam, it's not too difficult. Just do it by hand. Check your answers on MATLAB, by the way, by all means. Okay, so hopefully, okay, guys, it's getting a bit loud now. Right, hopefully we've got LU factorization down okay now. Now I'm going to throw the cat amongst the pigeons and tell you it's rubbish. We're going to look at something called LUP factorization. We're not going to finish this today. I'm going to have to carry it on in a couple of weeks, but we can start it. Okay, can anybody tell me why, when we do Gaussian elimination without partial pivoting, why it can be bad? Anybody know? Yes? Yeah. We could have an ill-conditioned system, which means doing Gaussian elimination just using type 3 row operations, which is adding a multiple of one row to another, that's liable to inaccuracies when we have to, because we're computational methods here, when we have to start truncating. Okay, so to get around that, we use partial pivoting when we do Gaussian elimination. Okay, we can convert our LU factorization to use partial pivoting, and this gives us LUP factorization. Okay, essentially, we're allowed, as well as using type 3 operations, we're allowing ourselves to use type 1. So we're allowing ourselves row swaps. So permuting 2 rows. If we allow ourselves row swaps, then the row swaps are applied to the A matrix. So we're going to factorize our system so that we have a matrix P times A is then equal to LU. So we're including our permutations on the left-hand side. Okay, this gives us all of these. Okay, these look complicated. I'll just explain what they are. Okay, your U matrix. Okay, these are all elementary matrices applied to our matrix A. Starting from just to the left of A, we assume we row swap, add, row swap, add, row swap, add, etc. So with partial pivoting, remember we want the pivot element to be the biggest number in the row. Biggest number in the column. So assuming we have to permute, okay, so we got our matrix A. First we do a row swap, and then we do an addition of one row to another. Then we do another row swap, then we do an addition. And we keep going in that pattern, permute, add, etc. until we get to row echelon form. If you do that, your U matrix is what you get left over in row echelon form. Your P matrix is the last permutation you did minus the second to last permutation you did, and keep going all the way down into the first permutation. That gives you this P matrix here. Now, U and P are quite easy to get for LUP factorization. L is a right nasty bugger, to tell you the truth. What you do for L's is you have a multiple of L1 times L2 times L3, etc. This is how many row operations you did. Now, L1, okay, if this I is 1 here, you start off with the inverse of A1, which is going to be your first addition. So it's that operation there. And either both sides of it, you have your permutations. So you have your Pi plus 1. So if I'm looking at A1 here, okay, I've got my P2, then I'd have P3, P4, P5 up to Pn. And on the other side, I'd have P2, P3, P4, P5 up to Pn. Okay, there is a proof of this method in the notes. I'm not going to go through it. I'll leave you to sort of do that on a Saturday night instead of going out. You can read through that. Okay, so let's have a look at an example. So what we're going to do, step-by-step example. Probably won't go through a worked example today. I'll leave that for next time. But this is something to leave you with. Determine our UP factorization of this matrix. Essentially, what we do is we apply elementary row operations with partial pivoting. So that means we want the pivot element to be the largest number in that column. So here, okay, this is my pivot element of 2. Okay, below it, we've got 6 and minus 4. So 6 is the largest absolute number. So I'm going to do a row swap between 1 and 2. Okay, gives me there. Then, okay, so I want this to be 0. So I've got 1/3 of row 1 subtracted from row 2. And I've got 2/3 of row 1 added to row 3. Okay, so those two operations there. Now, this is my pivot element. The 4 beneath it has got a bigger value, so I do a row swap. Okay, so swap the second and third rows. Okay, and then I want this one to be 0, so I subtract 1/4 of row 2 from row 1. This gives me my upper triangular matrix. So that's my U. That's in row echelon form. I stop the row operations. So hopefully you remember this in first year, partial pivoting. Okay, not as straightforward as non-partial pivoting, but you just have to make sure the pivot element has the largest absolute value in that column. That's the easy bit. Okay, we've done row operations. That's the simple bit. Right. Don't worry about it. I know this looks quite complicated. I'll explain. U, okay, so starting just to the left of A and going back this way, I have my pivot, adding, pivot, adding, pivot, adding. Okay, so what we had, okay, we had a pivot, sorry, permute adding, not pivot. Permute 1 and 2. So that's my permute 1 and 2. add a third, minus a third row 1 from row 2. That's that one there. Here, I didn't do any swapping between doing this one. Okay, so we assume a permute, add pattern. But between these two operations, I didn't do any swapping. There's no need. So what I do, or what you can do, is put the identity matrix there. Okay. Usually, I just ignore that bit there, but I've included it so that when we calculate P and L, it becomes a bit more obvious. Okay, so the next time we swap, we do 2 and 3. Oh yeah, sorry, we do the A3 1 2/3. Then we swap 2 and 3. And the last thing we do is minus a quarter row 2 from row 3. Okay, so that gives me my U's. That's my U there. Your P, okay, is P3 times P2 times P1. So this is my P1. That I is my P2. And P23 is my P3. Okay, usually I just ignore the I because multiplying by the identity matrix doesn't change anything. Okay, if you do those multiplication, and I've missed out a line of work in here, but that's what you get. Now we have to calculate the L's, and the L's are, yeah, they can be a bit nasty. I'm going to start with L3 actually because it's the easiest one. L3, okay, that's the last addition we did. The inverted. Okay, so that's the last addition we did. So if I find the inverse of that, okay, and that gives me my L3. Okay, so A3 2 1/4, so that's a quarter there. My L2, sorry, my second addition I did was A3 1 2/3. So if I invert that, I should have minus 2. Should have been minus there, by the way. As you can see, I've got it right there, but it should be a minus. But either side of that, I put the permutation that comes afterwards. So that addition was done, and then that permutation, that comes afterwards. So either side, I put P23. For L1, I do the inverse of the first addition, and then either side, I do P2 and then P3. But P2 is the identity, so I've ignored it here. So I have P2, which is I, so there should be an I there, multiplied by 2, 3. And on the other side, I have A2 1 1/3, I, then P2 3. So I'm just going to go back to this pattern here. So wherever I is, you go, so if I is 1, we go P2, P3, P4, etc. If I is 2, we go P3, P4, etc. So either side of your inverse A's, you have several P's. Okay. Put all them together, you get your L's. Okay, so essentially just overlay them. So that's minus 2/3. That there in row 3, column 1 is a third. Row 3, column 2 is a quarter. That gives you your L's. Okay. That takes practice getting used to that. It's not easy the first time you do it, but if you follow what we have there, it should all come out in the wash. Okay, I'm not going to go through the worked example. What you can do is once you've got this, if you multiply your P matrix by A and you multiply your L by U, you should get the same matrix. If you get that, you know you've done it correctly. Okay, so we're going to have a look at the worked example next time we meet in a couple of weeks' time, and we go through that.
When you do LU factorisation, LU is now going to